All right, so we're going to prove that theorem that I mentioned, which will be an easy way of checking if something is normal and if normal and finite. Some extensions are normal but not finite. For example, C over Q is normal because C has roots of everything. That's very much not finite. Okay. All right, so an extension will be normal and finite if and only uh, if and only if what? If and only if L, ooh, what happened here? There we go, oops. If and only if L over K is a splitting field. If L is a splitting field, for some polynomial over K. Okay, so it's an if and only if. What this is saying is, hey, if we know our extension is finite, we can ask, is this extension a splitting field? And if the is the big field a splitting field of some polynomial? If the answer is yes, then we automatically know the extension is normal. And that's going to be great because the fundamental theorem of Galois theory will apply to normal extensions in C. So this is going to be very helpful. So proof. Suppose for the forward direction, L over K is normal and finite. Since it's finite, it must be obtained from K by adding finitely many algebraic elements. So there exists alpha 1 through alpha r in L, algebraic over K. That was something we proved a while back. Finite if and only if algebraic, finite if and only if finitely generated by algebraic elements over K, such that L is K adjoin alpha 1 through alpha r. Let's set mi to be the minimal polynomial of alpha I over K. Then mi of t has a 0 in L because alpha I is 0. Since L is normal, it has all of its zeros. In L, right? Normality is an all or none condition. If you have 1, 0, you have all, and that's what it means to be normal. Okay, let's set f to be the product of the minimal polynomials. Then L is the splitting field for f over k. Because L is obtained by adding in some of the roots of f, but actually when you add in some of the roots, you add in all of the roots because it's normal. So L is the splitting field for f over k. Cool, so that's the forward direction. The forward direction is the easy direction. The reverse direction will be some work. So let's suppose, conversely, suppose L over K is a splitting field. For some polynomial G over K. Okay, what we need to show is we need to show the extension is normal and finite. Well, then L over K is finite, certainly, because we add in finitely many algebraic elements, namely the roots of G. And whenever you do that, you get a finite extension. So we just need to show it's normal. I say just need, but that's the hard part. So how do we do that? Well, let's take an irreducible polynomial f over k with 1, 0, and L. We then need to show it splits. Okay. Now what could happen? Well, it could not split, right? So let's let M be the splitting field of f over L, right? F is a polynomial over k. L is an extension of k. If we have coefficients in k, we have coefficients in the extension. So if it doesn't split entirely, we can enlarge f. We can enlarge L just a bit more to add in the remaining roots so that it does split. That's all that's saying. Let's suppose that we have two zeros. Theta 1, theta 2 are the zeros of f in M. Okay. M has all the zeros of f. We'll call them theta 1 and theta 2. Since f is irreducible, up to the leading coefficient, it is and theta 1 and theta 2 are zeros. F is the minimal polynomial of both theta 1 and theta 2. Okay, so this is all just set up, okay, right? So at no point did we prove anything. This is all just set up. We claim that the degree of L of theta 1 over L is the same as the degree of L of theta 2 over L. In particular, if this one is a 1, that is, if theta 1 is in L, that would make that extension degree 1, then the other one is 1. So if this one is 1, then the other one is 1. And that would tell us that theta 2 actually is in L as well. So if one of them is in L, the other one is in L, but these are arbitrary. So the thetas are arbitrary, so you get all roots in L. So that's where we're going with this. To do this, we're gonna look at two towers. So we're gonna consider two towers. And the two towers we're going to look at are k inside of k of theta 1 inside of L of theta 1 inside of M, and L, oops, it's not right, k inside of k of theta 2 inside L of theta 2 inside of M. Now, of course, if theta 1 is in L, this guy here is just L, but I mean, for the general claim, we don't know if this particular root is there. And similarly for theta 2. Okay, so we have our two towers. K is certainly contained in K adjoin something. And K is contained in L. So if I adjoin something to K, that should be contained in adjoining that same thing to L. And then M has everything involved here. Okay. All right. Great. So we have our two towers. And then what are we going to do? Well, we are going to look at the following. One second, where did it go? We are going to look at the following. We can imagine K first going to L of theta 1, or sorry, first going to L rather, and then going to L of theta 1. And then similarly here, we can imagine it going to L first and then adding them. And so we have sort of one way of going from K to L adjoin one of these thetas, and then we have this other way. So by the Tower law, the degrees of these extensions, the big extension, we can break them up in two different ways. So I'm going to use indices so I don't have to write out two equations. So for j equals 1 and 2, if I go from L of theta j to k, that's two different things. it's first go from L of theta j to K of theta j, and then go from, or I say go, but I mean the opposite way. First view the black font extension, or we can go from L of theta j from L, and then of course from K to L. Okay? And those are the same degrees. All right, now what do we know here? Well, this is true for both j equals 1 and 2. They're both equal. Both of these products are equal to each other. We also know that the minimal polynomial of theta 1 and theta 2 is f. So we actually know that when we add theta 1 or theta 2 to k, when we adjoin it, the degree is the same as if we were to adjoin the other one. So since f is the minimal polynomial, the degree of k of theta j over k is just the degree of f, right? It's the minimal polynomial of theta 1, theta 2 over k. All right, so now what? Well, there's one more thing that we have to do here. So these guys are the same for each j, but we also know that L of theta j is the splitting field of g over k of theta j. Now you might say, Bronson, I'm getting really confused, and that's fine. Let's go back and look here. L over k was the splitting field for the polynomial g over k. So L is obtained from k by adding in all the roots of g. Well, if I add in a random unrelated algebraic number to k and L with that new access to that new algebraic number still is obtained from k with access to that new number by adding in all the roots of g. So so this property is preserved by being a splitting field is preserved by adjoining a root. Okay, so what does that mean? Well, since k of theta 1 and k of theta 2 are isomorphic, the splitting fields are also isomorphic, and because the isomorphism that sends theta 1 to theta 2 leaves the coefficients of g alone, because the coefficients of g are in k. So L of theta 1 over k of theta 1 is isomorphic to L of theta 2 over k of theta 2 as extensions even. We really just need their degrees are the same, but they're isomorphic as extensions. All right, that was a lot. So what did we actually learn here? Let's go back up to our product. We learned that in this product, that is the degree of f. And irrelevant if this is theta 1 or theta 2, they're both the same number. Okay, so let's write that out. Let me say it like this. Then L of theta 1, k of theta 1, k adjoint theta 1 is the same as L adjoint theta 2, the degree of L adjoint theta 2 over k of theta 2. And let's call that common degree D. So what did we learn here? We learned that the degree of theta j over L times the degree of L over k is equal to, that's the bottom guy here, is equal to the degree of f, that's this guy on the right, times D. Or equivalently, the degree of L of theta j over L is D times the degree of f over the degree of L over k. Whew. All right. In particular, they're both the degree of L of theta 1 over L and the degree of L of theta 2 over L are equal to this same constant. So they are equal. That's the proof of the claim. That was kind of a lot. Okay, so you might want to go back and rewatch this. But This says then, or let me say so if theta 1 belongs to L and theta 2 is any other root of our polynomial f, L of theta 1 L is of course 1, but that's also L adjoint theta 2 L, the degree of L adjoint theta 2 over L. And so that tells us that theta 2 is also an L, because when you add it, you don't increase the degree. So must be, thus f has all roots in L. So L over K is normal, and we already showed it was finite. Ooh, that was a long one, but we got through it.